Today we are going to work with our learning target. I can apply the properties of integer exponents. So if you recall in years past when you were first introduced to values with exponents, we read our numbers as a base that has a smaller value to the right upper right corner of that base. That's our exponent. And how we evaluate that expression is we take the base, and the base is the value that's going to be multiplied by itself the amount of times that the exponent says. So in years past, we have been working with just single values. So if I have 5 to the third power, that would be the same as 5 times 5 times 5. And then we might have evaluated that and gotten the value 125. Today what we're going to be focusing on is when we have multiple bases and we need to simplify the expressions that we are given. So the first rule that we are going to look at is our product rule. So we're going to go through a few examples and then come up with what is the general rule that is the product rule. But first we want to understand how we come to that conclusion. So if I look at my expression here, I have 2 to the 4th power times 2 to the 2nd power. Well, 2 to the 4th power is the same as saying 2 times itself 4 times. And 2 to the 2nd power is the same as saying 2 times itself 2 times. So if I simplify that and I want to reduce this back into exponents, I see that I have 2, a base of 2, multiplied by itself 6 times. So we would say 2 to the 4th times 2 to the 2nd is equal to 2 to the 6th. In my second example, I have 4 to the 5th, which would be the base of 4 times itself 5 times, times the base of 4 times itself 4 times. And if I were to simplify that back into exponential form, I have a base of 4 multiplied by itself 9 times. If I look at another example, I have x to the 3rd times x to the 7. Well, x to the 3rd means x times itself 3 times. And x to the 7th means x times itself 7 times. And if I write that back in exponential form, I have a common base of x, and I have it multiplied by itself 10 times. So if I were to say x to the 3rd times x to the 7th is equal to x to the 10th. And in our previous example, I didn't finish this one out, 4 to the 5th times 4 to the 4th is equal to 4 to the 9th. And then in my last example here, I have 10 to the 5th, so that would be 10 times itself 5 times. And I am multiplying that by 10 to the 3rd, which is 10 times itself 3 times, which if I put that back into exponential form, I have a base of 10 multiplied by itself 8 times. So 10 to the 5th times 10 to the 3rd is equal to 10 to the 8th. So if you look through our examples here, I really want you to focus on what's happening with the exponents. What's the relationship? So we had 2 to the 4th times 2 to the 2nd, and that gave us 2 to the 6th. How am I going to go from having a 4 and a 2 to then getting a value of 6? Well, hopefully, if you haven't already figured it out, you're able to see that if I add those exponents, it will give me the value of that final exponent. So in my second example, 4 to the 5th times 4 to the 4th, 5 plus 4 is equal to 9. Third example, 3 plus 7 is equal to 10. 5 plus 3 is equal to 8. So when multiplying the common base, you multiply. Oh my gosh, no you don't. You add. And this is normally in class where I would say, what mistake do you think is the most common for kids to make? So as I was saying, that is a very common mistake. A lot of times students see the product rule and they say, oh, if I'm multiplying the bases, then I multiply the exponents. That is not true. When you multiply the common base, you add the exponents. Moving on, if we look at the quotient rule, this comes into play when we are dividing our common bases. So again, if I'm looking at expanding the expression that I'm given, I have 4 to the 5th, so that would be 4 times itself 5 times. And I would be dividing by 4 to the 3rd, which would be 4 times itself 3 times. And the one thing I want you to look and focus on here, when I have a numerator divided by the same value in the denominator, we want to remember that that creates a value of 1. So 4 divided by 4 is 1. 4 divided by 4 is 1. 4 divided by 4 is 1. And then the value that I am left with is 4 to the 2nd power. So 4 to the 5th power divided by 4 to the 3rd power is equal to 4 to the 2nd power. If I look at my next example, 7 to the 12th power divided by 7 to the 7th power. So we have 7 times itself 12 times. Divided by 7 times itself 7 times. Okay, and then we want to see how many values can I reduce to 1. And we have 7 values that I can reduce to 1. And then that leaves me with how many 7s being multiplied by themselves. So that would be 7, 1, 2, 3, 4, 5, 7 to the 5th power. So 7 to the 12th power divided by 7 to the 7th power is equal to 7 to the 5th power. If I look at my third example, I have y to the 10th. Y to the 10th would be y times itself 10 times. Divided by y to the 3rd. So y times itself 3 times. And if I see how many y's are being divided by themselves, that reduces to 1, 3 ones, 1 times 1 times 1, and then I am left with y to the 7th power. So y to the 10th divided by y to the 3rd equals y to the 7th. And last but not least, we have 8 to the 8th power divided by 8 to the 3rd. So if I expand my multiplication or my exponents, 8 to the 8th power, it would be 8 times itself, 8 times, divided by 8 times itself 3 times, and that leaves 3 sets of values that reduce to 1, which would leave me with 8 to the 5th power, 8 times itself 5 times. So we would say that 8 to the 8th divided by 8 to the 3rd is equal to 8 to the 5th. Now again, if you haven't already noticed, there definitely is a pattern that's happening. So how am I going to go from an exponent of 5 to the exponent of 3 to then the exponent of 2? What relationship do those values have? Or 12, 7, and 5, 10, 3, and 7, 8, 3, and 5. Well, in case you haven't already figured it out, when dividing the common bases, you subtract the exponents. So 4 to the 5th divided by 4 to the 3rd would be the same as 4 to the 5 minus 3, which equals 4 to the 2nd power. 7 to the 12th divided by 7 to the 7th power would be 7 to the 12 minus 7, which would give us 7 to the 5th, and so on. Moving on, we sometimes have values that are raised to a power, so they already have an exponent, and that exponent is then going to be raised to a higher power. So if we look at our first example, we have 5 cubed, and then that 5 cubed expression is squared. So that would look like 5 cubed times itself twice. And then using our product rule from earlier, when I'm multiplying a common base, I am going to add the exponents, which would then give me the value of 5 to the 6th power. So I have 5 to the 3rd squared is equal to 5 to the 6th. If I look at my second example, I have 7 squared raised to the 4th power. So that's like saying 7 squared times itself 4 times. And again, if we remember our product rule, since we're multiplying all of our common bases, we would add all of our exponents, which would leave us with the answer 7 to the 8th power. So we could say that 7 squared raised to the 4th power is equal to 7 to the 8th power. On my next example, we have 2a raised to the 3rd power. So that's like saying 2a times 2a times 2a. So I have 2a times itself 3 times. And I'm going to rewrite this a little differently. I'm going to pull all the 2's out in front. So 2 times 2 times 2 times a times a times a. And when I do that, I see that I have 2 times itself 3 times, so that would be 2 to the 3rd power. And then I have the common base a times itself 3 times, which would be a to the 3rd power. So we have 2a raised to the 3rd power is equal to 2 to the 3rd power and a to the 3rd power times a to the 3rd power. On our last example, we have 1/3 raised to the third power. So we would take our common base of 1/3 and we would multiply it by itself 3 times. Okay, and then if I look at my numerator, I have 1 times 1 times 1, which would be 1 to the third power. And then my denominator, I have 3 times itself 3 times, 3 to the third power. Now we really wouldn't leave 1 to the third power. That we would traditionally just simplify to 1. However, we could leave it as 3 to the third power in the denominator for this purpose of this lesson. So we would say that 1/3 cubed is equal to 1 over 3 cubed, or 1 to the third over 3 cubed. So when raising a power to a power, this is when you are going to multiply the exponents. So if you notice in our first example, we had 5 raised to the third to the second. Well, 3 times 2 is equal to 6. In our second example, we have 2 times 4 is equal to 8. Now in our third example, we have to remember that even if we don't see an exponent, there is always a 1 there. So this would be like saying 1 times 3, that would give us 2 to the third, and then 1 times 3 gave us a to the third. And then in our last example, again, remembering that there are those invisible ones, so it would be 1 to the 1 times 3, which would give us 1 to the third, which gives us 1, and then 3 to the 1 times 3, which is 3 to the third power. Negative exponents sometimes can be a little challenging because we do have to do a little more conceptual work, but we'll start with just our expanding it to help us see why what we're about to do actually does work. So 4 to the third power is 4 times 4 times 4. And then 4 to the fifth power is 4 times 4 times 4 times 4 times 4. So if I look at those values that can reduce to 1, all of those numerators and denominators reduce to 1, you'll notice there's nothing left in the numerator. However, that's not true. There is something left there, but again, the only value that we can get away with not writing, but is actually there, is 1. And so this would reduce to 1 over 4 to the second power. But let's remember back to when we did our quotient rule. We took 4 and we subtracted our bases. I'm sorry, we subtracted our exponents. So we had common bases and we subtracted the exponents. Well, 4 to the 3 minus 5 would give us 4 to the negative second. These two values are equal. So anytime you have a negative exponent, you're going to want to move it across the fraction bar and it will change the sign of the exponent to positive. So if we look at our second example, we have x to the 9th divided by x to the 12th. So if we write that all out, we'll notice that again, all of my x values in the numerator cancel to 1, so I'm left with a 1. And then I'm left with x times itself 3 times in the denominator. So that would be 1 over x to the third power. But if I were to do my quotient rule, I would do x to the 9 minus 12, and I would see that that would be equal to x to the negative third. So again, when I have that negative exponent, I can put it into a fraction, and it's going to change my exponent positive. Now be careful, you always want to try if you can do a product or quotient rule first, because sometimes you'll have an example like this third one here, where we have 7 to the negative third raised to the negative second, And we already talked about that when we raise a power to a power, we're going to multiply the exponents. And if I multiply those, a negative times a negative is going to give me a positive. And then I'm not going to flip it over the fraction mark because it's already positive, which is what we wanted. And then on our last example here, we have 3 to the 4 minus 5. So I'm dividing our common bases, which would give me 3 to the negative first. So I would put a 1 over the fraction, or I'd put it into a fraction and move it to the denominator. My exponent would become positive, and it would just become 1 over 3 to the first, which is 1/3. Our last rule is the zero rule. And this one is pretty straightforward. Any base except 0 raised to the 0 power is going to be equal to 1. So x to the 0 power equals 1. 3 to the 0 power equals 1. Now be careful on this third one because notice 2 does not have an exponent of 0. 2 still has that exponent of 1. So this simplifies to 2 times y to the 0, which is 1. So that just becomes the value of 2. And then same here, 3 has an exponent of 1, y has an exponent of 1. So it would be 3 times x to the 0, which is 1, times y to the first power. So that would just be 3y.